If the uniformly loaded rectangular slab is supported on all four edges, the UDL will be transferred to all the four supporting edges. Then the slab will bend along the two orthogonal direction as shown here. This action is called as two-way action. When the aspect ratio of long span to short span is less than 2, then the values of curvature and moments along the short and long span is significant. In this case, the slab is termed as two-way slab. According to the clause 24.4, the slabs spanning in two directions at right angles and carrying UDL can be designed by any acceptable theory or by using coefficients given in Annexure D of IS 456-2000. In case of uniformly loaded two-way rectangular slab, the code suggests design procedures for two types of slab. First type is torsionally restrained slab. In this type of slab, corners are restrained from lifting up and edges may be continuous or discontinuous. The slab supported by beam column system will come in this category. The slab supported by brickwork and uplifting of slab corners is restrained by wall over the slab or any other system will also come in this category. So, this torsionally restrained slab will be designed as per the clause D1 of the IS code. Second type is simply supported slab whose corners are free to lift up. The slab supported by brick wall without any restraining arrangements will come in this category. This type of slab will be designed as per clause D2 of this IS code. So let us learn the complete design of simply supported two-way slab supported by the brick wall with the help of numerical example as per IS 456-2000 code provisions. So watch this video till the end to understand the design concept visually in most simplified way. Subscribe this channel and press the bell icon so that you can get all notification of the new videos. So let us design a simply supported RCC slab for a room floor having following data. Clear dimensions of the room is 4 meter by 5 meter. Width of supporting brick wall is 230 mm. Live load on the floor is 3 kN per meter square. Floor finish is 1 kN per meter square. The grade of concrete is M20 and grade of steel is Fe415. The corners of the slabs are free to lift up. To start with the solution, let us decide whether slab is one way or two way. As per SP 34 clause 9.3.1, when the slab is supported on four sides and aspect ratio of long span and short span is less than or equal to 2, then slab will be treated as two-way slab. We have longer span as 5 meter and shorter span as 4 meter. The ratio of a longer span to shorter span is equal to 1.25, which is less than 2. Hence, this slab will be treated as two-way slab. In first step, let us assume the thickness of slab based on the deflection criteria. Notes in the clause 24.1 gives the span to depth ratio for the two-way slab of the span up to 3.5 meter. As the short span of this slab is 4 meter, hence the span to depth ratio given in the clause 23.2 will be used. As per this clause, the span to effective depth ratio for the simply supported slab is 20. Since the percentage of reinforcement in slab is generally low in the range of 0.3 to 0.5%, a span to depth ratio of 25 to 30 is more appropriate by considering the modification factor for Fe415 steel. So consider the span to depth ratio equal to 30. As per the notes given in clause 24.1, for the two-way slab, the shorter of the two span should be used for calculating the span to effective depth ratio. After rearranging the equation and solving, we get effective depth D equal to 133 mm. Assume clear cover of 20 mm for mild exposure and diameter of bar as 10 mm. Here we need to find the effective depth and cover in short and long span. So let us first find the effective cover to bars along short span, which is equal to 25 mm, and effective cover to bars along the long span equal to 35 mm. Assume total depth of slab equal to 165 mm. Hence, the effective depth for short span is equal to 140 mm and that for long span equal to 130 mm. In step 2, let us calculate the effective span of the slab by referring to clause 22.2 of IS 456. As per the clause, the effective span of the slab shall be taken as clear span plus the effective depth of the slab or center to center of the support, whichever is less. Hence, let us calculate first clear span plus the effective depth of the slab. The short effective span Lx is equal to 4.14 meter and long effective span Ly is equal to 5.13 meter. The center to center of supports for short span is 4.23 meter and for long span it is 5.23 meter. Adopt effective span equal to least value between first and second. Hence, short effective span is equal to 4.14 meter and long effective span is equal to 5.13 meter. In next step, let us calculate the loads per unit area acting on the slab. First, calculate the self weight or dead load of a slab by multiplying the thickness of a slab with concrete density. After putting the values of slab thickness and concrete density, we get dead load of the slab as 4.13 kilonewton per meter square. Next, floor finish of the slab is given as 1 kilonewton per meter square. Now, calculate the total dead load by adding dead load of a slab and floor finish. This is equal to 5.13 kilonewton per meter square. The live load on the slab is given as 3 kilonewton per meter square. After getting dead load and imposed load, compute the total design or factored load per unit area using a load combination of dead load plus imposed load with a partial safety factor of 1.5 as given in table 18 of IS 456. Thus, the total design or a factored load per unit area equals to 1.5 times dead load plus 1.5 times imposed load. This is equal to 12.2 kilonewton per meter square. In next step, let us compute the design moments. When simply supported slabs do not have adequate provisions to resist torsion at corners and allowed to lift up, then design moments per unit width will be calculated based on the equations given in clause D 2.1. For the calculation of design moments, unit width strip at midspan for short span and long span are considered. The alpha x and alpha y in the moment equations are the bending moment coefficient, which can be computed by two methods. First, by using Rankine-Grashof method formulas as shown in equation 1 and 2, or second, by using the values given in table 27 of clause D 2.1. In this table, values of alpha x and alpha y are given for different values of Ly by Lx ratio. The alpha x and alpha y can be computed for the calculated Ly by Lx ratio using linear interpolation formula. So let us use the table 27 to find the coefficient alpha x and alpha y. For this, we need to calculate the value of Ly by Lx ratio, which is equal to 1.239. This value is between 1.2 and 1.3. Accordingly, compute alpha x and alpha y using linear interpolation formula. After computation, we get alpha x equal to 0.0878 and alpha y equal to 0.0571. After putting all the values required in design moment equation and solving, we get short span moment equal to 18.36 kilonewton meter and long span moment equal to 11.94 kilonewton meter. Next, it is required to check the adequacy of the assumed depth of the slab for maximum design moment. For this, use the expression given in section C of clause G 1.1. In this equation, mu lim is the maximum value of design moment. Xumax by D is 0.48 for Fe415 as per the clause 38.1 and small b is the width of design strip equal to 1000 mm. In this equation, depth D is unknown. After putting all the values in the equation and solving, we get the required effective depth as 81 mm for the maximum design moment. This is less than the provided effective depth, hence safe. After knowing the adequacy of the thickness of slab, let us compute reinforcement on the tension side of the slab in next step. The area of a steel required for the design bending moment can be calculated by referring the formula given in clause G 1.1b, annexure G of IS 456-2000. This formula results in quadratic equation. Otherwise, you can also use the simplified equation number 2 to calculate area of a steel. Let us use equation number 2 to compute the required area of a steel. As the slab is two-way slab, we need to find the area of a steel along the short span and along the long span also. So let us start with steel required along short span. In the equation, value of a B is equal to 1000 mm, while effective depth D equals to dx, that is 140 mm. After putting all the values and solving, we get the area of a steel equal to 385 mm square per meter. Similarly, calculate the steel required along long span. In the equation, value B is equal to 1000 mm, while effective depth D equals to dy, that is 130 mm. After putting all the values and solving, we get the area of a steel equal to 265 mm square per meter. Now, let us check the minimum area of a steel required. Hence, as per clause of IS 456, the minimum area of a steel required is 0.12% of gross cross-section area of the slab for Fe415 bars. After calculation, we get minimum area of a steel equal to 198 mm square, which is less than the required area of a steel for short span and long span. Let us fix the diameter and spacing of the bars to be provided along short span. So, select the bar diameter as 10 mm. The cross-sectional area of this bar is 78.5 mm square. Now, compute the spacing of bar by considering 1 meter width of a slab. Here, we get the spacing equal to 203 mm. But as per the clause 26.3.3, the maximum spacing of the bar is 3 times the effective depth of slab or 300 mm, whichever is smaller. So Let us calculate the second value of spacing equal to 3 times effective depth, which is equal to 420 mm. And the third value of spacing is equal to 300 mm. Now, maximum spacing permitted is equal to the minimum value of the first, second and third value of the spacing. This is equal to 203 mm. Adopt the spacing of the bar as 175 mm. Similarly, fix the diameter and spacing of bars to be provided along long span by selecting 10 mm diameter of Fe415 bars. The calculated spacing of the bar is 296 mm. Next, calculate the second value of maximum allowable spacing equal to 3 times effective depth, which is equal to 390 mm. And the third value of maximum allowable spacing is equal to 300 mm. Now, the maximum spacing permitted is minimum of first, second and third spacing, which is 296 mm. Hence, adopt the spacing of the bar as 250 mm. So, provide 10 mm dia bar at 175 mm center to center along the short span with alternate bars bent up at support. Hence, the area of a steel provided along short span is 448.57 mm square per meter, and provide 10 mm dia bar at 250 mm center to center along the long span with alternate bars bent up at support. Therefore, the area of a steel provided along long span is 314 mm square per meter. In next step, check the adequacy of provided depth for the deflection control. Based on clause 23.2.1 for simply supported slab, the formulation to compute the depth required for deflection criteria is shown as equation number 1. In this equation, effective span will be for short span and MF is modification factor, which is to be calculated from the figure 4 of clause 23.2.1. So, let us compute modification factor. In the graph, x-axis shows the percentage of tension reinforcement and y-axis shows modification factor for corresponding reinforcement. So, let us compute the percentage of a tension steel provided along short span. This is equal to 0.32%. Next, compute the value of a steel stress at service load Fs from the formula given in figure number 4. After putting all these values in the equation, we get Fs equal to 206.58 Newton per mm square. So, from the graph, modification factor can be calculated as 1.75. After putting all the values in equation 1 and solving, we get the depth required for deflection criteria, which is equal to 118 mm. This value is less than the effective depth provided in short span. Hence, it is safe. In next step, check the feasibility of the slab section and reinforcement for the shear stress. The critical section for the one-way shear in two-way slab is at a distance of effective depth D from inner face of the support as shown in figure. So, let us compute the shear force at this critical section. The maximum factored shear force per unit width will be calculated using equation 1. In this equation, effective depth D is the average depth of 135 mm. After putting all the values and solving, we get shear force Vu equal to 22.75 kN. The nominal shear stress due to shear force is obtained by using equation in clause 40.1 of IS 456. In the equation, value of B is equal to 1000 mm and effective depth D is average depth 135 mm. After putting all the values and solving, we get tau V equals to 0.168 Newton per mm square. Now let us compare this shear stress with the design shear strength of the slab. We can get this design shear strength based on the percentage area of a steel provided at support and the grade of a concrete from table 19 of IS 456. So let us find the percentage area of a steel provided at support. In this, the value of AST is the area of a main steel provided at support at bottom, which is equal to 224 mm square. By providing the value of AST, width B and average effective depth D, we get the percentage of a steel PT as 0.16%. In table 19, the percentage value PT is lying between 0.15 and 0.25. Hence, the value of tau C is also between corresponding values 0.28 and 0.36 for M20 grade of concrete. Here, we can calculate the tau C by using linear interpolation formula. So let us mark the values of x1, x2, y1, y2, x and y by putting all these values in the interpolation formula. We get y equal to 0.29, which is the value of tau C. As per clause 40.2.1.1 for slab, the design shear strength is equal to tau C into K, where K is based on overall depth of slab. This slab is 165 mm thick. Therefore, the value of K can be computed using linear interpolation, which is equal to 1.27. After multiplying tau C with K, the shear strength is equal to 0.368 Newton per mm square, which is more than the shear stress. Therefore, this slab is safe in shear. Finally, let us summarize the design and the reinforcement detailing. A simply supported two-way slab is designed with M20 grade of concrete and Fe415 steel. The thickness of slab is 165 mm. Along the short span, provide 10 mm dia bars at 175 mm center to center with alternate bar bent up at support. And along long span, provide 10 mm dia bars at 250 mm center to center with alternate bars bent up at support. If you like this video, then share your thoughts in comment section. Subscribe this channel and press the bell icon to get the notification of such interesting videos for visual and simplified learning of various civil engineering topics.